Universitas Jember plays its central role to develop science and technology in various sectors such as plantation, agriculture, maritime, health, tourism, industry, arts, and culture. The agriculture and plantation sectors have made Jember famous for its coffee, sugarcane, tea, tobacco, cocoa, and edamame soybean. Jember is also culturally unique, with diverse mix of Javanese, Madurese, Osing, Chinese, and Arab culture. 4 national parks which become nature laboratories to develop science. Rich and abundant natural resources provide history and phenomena for potential researchers. The potential research and the development of knowledge generate scientists in their own field. Professor Bambang Sugiarto, expert in biotechnology and genetics engineering. Professor Bambang Kuswandi, expert in analytic chemistry, chemosensor, and biosensor. Professor Ahmad Subagio, expert in biotechnology, food sciences, and nutrition. Professor Rudy Wibowo, expert in agricultural economics. Professor Nawianto, expert in economic and environmental history. Professor Slamin, expert in graph theory. Professor Dafik, expert in combinatorics, graph theory, and combinatorial education. Professor M. Arif Amrullah, expert in criminal policy and economic criminal law. Aditya Wardono, PhD, expert in Asian monetary, financial, and development economics. Dr. Kartika Sanjarini, expert in molecular biology. Abu Bakar Ebihara, PhD, expert in international relations. By 2018, the university has vast range of programs to choose from 15 faculties, 27 postgraduate programs, and 73 undergraduate studies. To support the objectives of education, research, and community service, and to optimize the nature laboratory potentials around Jember, the university has developed and established branch campuses in 2 nearby towns, Bondowoso and Lumajang, which enables a well-built
Cek. Cek. Bisa sayangnya.
"52 years of endless hard work, of prolonged dedications, of persistent efforts, for the best experiences, for advanced knowledge, for outstanding researches, achievements to create a better future."
Jember berada di tengah-tengah di jantung wilayah perkebunan. Area perkebunan di sini memberikan bahan-bahan yang luar biasa kaya untuk bisa meneliti mengenai pengetahuan masa silam. Itu saya kira jadi alasan penting bahwa sumber sejarah itu bisa dikumpulkan di sekitar Universitas Jember.
Budaya Pendalungan ini merupakan budaya baru yang saya belum pernah ketemu, dan saya bisa ketemu budaya itu hanya di Jember.
It's the whole thing because I think how Asia is so interesting and it's complete different to Europe, and I was really interesting, or I'm really interesting in the culture and the religion and how it impacts the life here, the life and the university.
Karena pariwisata, harus sangat konten ya Jember, tambah iane harus sering lau halimar ba pantai-pantai newe Jember. Depois nya wisata mos termasuk diak dibandingin husi paten sersi seluk. Hoi dane hal-hal tertarik nomos hakarak halau studi nafating lanjut ya Universitas dari Jember dane.
Ini yang luar biasa berpotensi itu adalah karena UNEJ ini mempunyai akreditasi A. Kemudian semua keilmuan yang ada saat ini itu ada di Universitas Jember.
Jadi di sini saya melihat bahwa range ilmu itu sangat banyak sekali kalau orang datang ke sini, juga didukung oleh lingkungan Jember yang mungkin tidak seperti di kota-kota besar yang terlalu banyak kalau buat mahasiswa itu terlalu banyak godaan.
Pada awalnya saya tidak membayangkan keadaan Universitas Jember itu seperti apa. Namun setelah saya berkuliah di sini, persepsi saya tentang Universitas Jember jauh dari apa yang saya pikirkan. Universitas Jember memiliki banyak potensi yang mendukung potensi saya sendiri, baik dalam pendidikan maupun seni ataupun olahraga.
Kita biasanya hanya melihat dari luarnya aja, dengan banyak sharing, kemudian kuliah, juga pekerjaan di laboratorium. Di situ yang sangat memacu saya bahwa ternyata masih sedikit yang saya tahu, sehingga saya harus lebih banyak belajar lagi.
Kalau Anda ingin belajar perkebunan, kopi, kakao yang ada hanya di sekitar Universitas Jember. Tidak akan ada yang lain, karena pusat penelitian kopi dan kakao hanya ada di Jember. Satu-satunya di Indonesia. Ya, dari segi agro ya, maka tidak ada tempat lain untuk belajar tebu kalau nggak ke Universitas Jember. Dalam hal biologi yang terkait dengan tropical resource ya, kita punya hal yang lebih lengkap, tidak sekedar daratan, tapi kita juga punya pantai, kita juga punya laut, dan kita mengeksplorasi semua itu. Dalam hal kesehatan ya, kita berbeda. Yang lain bicara tentang patogen, kita bicara tentang vektor. Nah, jadi dari situ mestinya orang berpikir ya, saya tidak ada tempat yang lain untuk belajar kecuali saya datang ke sini.
Assalamualaikum. Okay, Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. First of all, please introduce myself. My name is Samantha as the Master of Ceremony on this event today. Before we start, let us pray and praise God because of His bless and mercy. We can come together without any obstacles to this event with healthy condition in the 2021 UNED Summer School on Bio-Based Chemical Series 2 with the first topic, Functionalized Bio-Based Polymers and their application, and the second topic is Integrated Recovery for Bioenergy Production. Before we come into the main session, let us pray first so the event that we will hold on this day will run well. Pray based on individual belief begins. Dan, to Honorable Dr. Jakapon Pantuwangpaki as speaker, to Honorable Dr. Rizky Fitria Darmayanti as speaker, to Honorable Dr. Insinyur Tri Wahyu Hadianto STMT as Dean of Engineering Faculty Universitas Jember, to Honorable Insinyur Boy Ari Fahri STMT PhD as Head of Chemical Engineering Department Universitas Jember, to Honorable Lecturer from Chemical Engineering Department Universitas Jember, and to all honorable distinguished guests. Ladies and gentlemen, on this nice occasion, let me convey the rundown of the event today as follows. First, opening. Second, singing Indonesia Raya. Third, the opening speech from Dr. Insinyur Tri Wahyu Hadianto, STMT. Fourth, the 2021 UNED Summer School on Bio-Based Chemical Series 2, with the first topic, Functionalized Bio-Based Polymers and their application, which will be delivered by Dr. Jakapon Pantuwangpaki. Fifth, discussion or the question and answer session. Sixth, second topic, which is integrated recovery for bioenergy production, which will be delivered by Dr. Rizky Fitria Darmayanti. Seven, discussion or the question answer session, and the last is closing. Ladies and gentlemen, now we like to give time for Dr. Insinyur Tri Wahyu Hadianto STMT for the opening speech. To Dr. Insinyur Tri Wahyu Hadianto, time is yours.
Okay, thank you very much. The Honorable, can you hear my speak? Can you hear? Hello?
Yes.
Okay.
Yes.
Okay, the Honorable Dr. Jakapon Pantuwong Pakdi from Japan Advanced Institute of Science and Technology, Japan, and Dr. Rizky Fitria Darmayanti from Chemical Engineering Department, University of Jember, Faculty of Engineering, and also Dr. Matu as a moderator, and also Dr. Boy Arif Fakri as the head of the Chemical Engineering Department, and also Dr. Hanggara Sudrajat as the chair of the summer school, and our colleges at the Faculty of Engineering, and our students. And I would like to welcome you all to the 2021 UNED Summer School on Bio-Based Chemicals, which will be delivered fully online. In an ideal setting, I would meet and greet you in the lecture hall. However, due to the current regulation for infection control in response to the coronavirus SARS-CoV-2 pandemic, it's not possible for us to gather offline. Hence, I welcome you just warmly with this online platform. Before I officially open this event, please let me to introduce us that the Faculty of Engineering Unit of Jember, we have 16 study programs. One of them is chemical engineering. The Faculty of Engineering University of Jember is located in the west of the island of Bali, and we are and we are the eastern part of the island of Java. We have around 2,300 students and 1,130 lecturers and researchers, and we founded in 1999. The vision of the Faculty of Engineering University of Jember is to become an excellent faculty in the field of environmentally sound technology and industrial agriculture. Therefore, it's obvious that such an international summer school on biomass-based chemical products can be one way to realize the university vision, our faculty. The theme of the summer school is from biomass to advanced chemical and bioenergy. The proposed theme is in line with the intention of Faculty of Engineering Universitas Jember to specialize its research direction to agro-industrial technology. And the theme is also highly relevant to Indonesia because biomass is the most promising sustainable feedstock for chemicals and energy products in our country. This summer, school addresses the question of how to efficiently transform biomass to advanced chemicals and bioenergy. This school invites 7 lecturers from Taiwan, Japan, Indonesia, Austria, Italy, Thailand, and United Arab Emirates to deliver their important insights. Finally, I would like to officially open the 2021 UNED Summer School on Bio-based Chemicals, which is organized by our Chemical Engineering Department. We expect this event to be a pleasant platform for exchanging ideas to generate novel insight and to produce impactful collaboration in the near future. Please enjoy the summer school. Thank you very much for your attention and cooperation in advance. Thank you very much.
Okay, thank you for Dr. Engineer Tuhayu Hadianta as the opening speech. Now we are going to singing our national anthem Indonesia Raya. So all the guests are expected to be prepared.
Go.
Yes, and when you
Ladies and gentlemen, now we are coming into the main event, the 2021 UNED Summer School on Bio-based Chemicals, Polymers, and on Bio-based Chemicals Series 2 with the first topic, Functionalized Bio-based Polymers and Their Application, which will be guided by Dr. M. Maktoum Muharji Al-Fajri. To Dr. M. Maktoum Muharji Al-Fajri, as moderator, time is yours.
Okay, thank you, Master of Ceremony, Samantha, for the opportunity given to me. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Welcome to the 2021 UNEJ International Summer School on Bio-based Chemical Series 2. It is a Young Scientist Series. Today, we have Dr. Jaka Pontuwong Pade and Dr. Rizky Fitria Darmayanti with us here. Good morning, Dr. Jaka and Dr. Rizky. I hope you and your family are always healthy in this COVID-19 pandemic. Ladies and gentlemen, allow me to introduce myself. My name is Maktoum Muharji. I'm a lecturer at Chemical Engineering, Universitas Jember. It is a big honor for me. Dr. Hanggara Sudrajat, as a chairman of this summer school, gave me an opportunity to be a moderator today in Summer School Series 2. Okay, before starting today's session, I'd like to inform you that if you have a comment or questions, please kindly use the Google form. I guess the operator will provide the link here in Zoom chat. You can put your comment and question there. Ladies and gentlemen, this event will be divided into two segments. Firstly, Dr. Jaka from the Japan Advanced Institute of Science and Technology will present about functionalized bio-based polymer and their application. Secondly, we have Dr. Rizky from Universitas Jember will present about integrated recovery for energy production. The given time, every lecture will last about 60 minutes. 40 minutes will be allocated for the presentation and 15 minutes will be allocated for the discussion section. So, our first lecturer is Dr. Jaka Pontuwong Pade. Let's begin this segment with the performance from Dr. Jaka. The operator, please present by a slide CV from Dr. Jaka. Okay, ladies and gentlemen, Dr. Jaka Pontuwong Pade is a researcher at the Japan Advanced Institute of Science and Technology, JAIST. He obtained 2 PhD in material science from JAIST and also in engineering and technology from Sirindorn International Institute of Technology, Thailand. His research area include functionalized biopolymer. He successfully created sugar-derived polyamide bearing quaternary amine functional group and discover an anion absorption ability to anthocyanin containing biomass in the water environment. Okay, ladies and gentlemen, please join me in welcoming Dr. Jaka. Dr. Jaka, time and screen is yours.
Hello, can you hear me? Thank you so much, Dr. Maktoum.
You're welcome.
Right. Thank you so much. I am Jaka Pontuwong Pade. I understand this last name is very long because I'm actually from Thailand, but yes. I was working in Japan. So today I'm going to actually talk about the work that I have done in Japan. Okay, so today is functionalized bio-based polymers and their applications. Okay, and you can see that I'm going to go through 5 chapters today. Let's don't talk about the chapters here. Let's go on to the general introduction first. I want to start with a very light notes and talking about myself just a little bit. Okay, I'm actually graduated in bachelor degree from the environmental science in the University of Oregon, USA, and then my MSc is still in urban water engineering. It's more like environmental science too in the UK. So you can see that I actually started on the biology, environmental science things. And it's quite important for the story I'm telling here because I'm coming to the PhD and doing something very, very different. I'm just showing the very nice pictures here because afterward it's going to be something that's very, very science. So here, these are my bachelor's master, and this is the dual degree that I have done. I actually finished the one from Japan and from Thailand this year, just a month ago, and the one from Japan just 1 year ago that I finished. Okay, so you can see that this is the dual degree things. I don't know why anyone would want a dual degree in PhD. I mean, you just need only one PhD, right, in your life actually. But because of the programs, that's why I am doing 2 degrees right now. And one is in biochemical engineering and another one is in material science in Kaneko Laboratories, Thammasat University in Thailand, and Japan Advanced Institute of Science Technology, because JICE in Japan. For today's lecture, I'm going to talk about JICE only, okay? Oh, sorry, and right now, I'm actually based in Bangkok right now and doing my family business based in water purification system. And I'm also a part-time lecturer in Thammasat University and also some secondary school as well, teaching general science, biology, chemistry, and all these, okay? So you can see that I'm talking about the mechanical laboratory work. So I'm going to here in the lab, okay, over there, sorry, in Japan, in JICE, we are mostly doing about bio-based polymers and cyanobacterial engineering, okay? So we have 2 main groups in this lab. I'm the one in the bio-based polymers, okay? But in the cyanobacterial engineering, there are very important bio-based materials as well. They even make some kind of products to sell, okay, in Kaneko Laboratory. And for me today, that's why let's go on to the main title, which is the bio-based polymer. Now, when we talk about bio-based polymer, it's very important to know that it's coming from the bio-based sources, going to be the weeds, corn, or even algae, right? Sometimes we make a monomer out of these renewable resources. And then we make these monomer into bio-based polymers, right? For example, PHA, PLA. I think many students are in here. So if I'm going too fast for the students, please leave me the comments or questions, okay? And okay, let's continue then. Sometimes, okay, monomer into polymers, I think this is just basic chemistry, but sometimes you can also direct convert them, okay? We call this direct conversion as first generation biopolymers. For example, alginate. I know it's macromolecular alginate. It's not really a polymer per se, but we can call it the first generation biopolymers. Okay, something like alginate, yeah. Yes, all these, and even monosaccharides and all these things, okay? But there are some problems with these bio-based polymers today because we don't have the performance compared to the conventional polymers, okay? And what are the conventional polymers? Polyethylene, for example, very strong, right? And that's the problems. But the thing is, we want high performance. We want the recyclability. We want to stock CO2. So it's have to have high performance. So we can use it many, many times, right? And because we want to help the world for the global warming situation here. So that's why bio-based polymer is very important. And in order to achieve this, okay, my research themes, it's going to mix the biopolymers with the inorganic substances. And I'm calling it the organic inorganic composites, okay? Now, we have a lot of organic inorganic composites in the study today. And after studying hundreds of papers and all these things, I know that we have to study a lot of papers. I got to divide these composites into 4 different kinds, main different kinds, okay? I just going to put tell everyone here are the inorganic composites that are functional. So there are functional groups that have been added into the main chain of the polymer. For example, here we got the PLA, right? And we got this fluorine embedded into this polymer, and it can be used for water contact angle and antibacterial properties, which wasn't be able to use by PHA alone, right? And we can do direct mixing here. Okay, sorry, just now we call it the halogenation because we add chlorine, fluorine into the polymer. We got direct mixing to create things that have the tensile strength of flame retardancy materials. We can also do metal incorporations in order to create electrical or adsorption properties polymer or even quaternizations, okay? Now here are in the studies, we also still struggling with the higher performance of the polymers. Now, when I went to the Carnegie laboratory, I was tasked with this polymers, okay? Out of nowhere, we call teacher in Japan sensei, okay? I call him Kaneko sensei. Kaneko sensei just tell me, hey, we got 4-aminosinic acid here, and this can be derived from glucose, okay? We made it into corisomate. We do the bacterial we do the bacterial degradations, make it into PA using the ABC bacteria here, and then we create 4-aminocinamic acid here, and you can also create some kind of monomers that make it into the polymers later. But then I'm a bit perplexed, and I don't know what to do because I'm coming from environmental science department. So I'm looking at this monomer that created from glucose here, 4,4-diaminotetracyclic acid. Is glucose based? What can I do with it? Okay, so let's look at its molecular design. It's very important when we look at its molecular design when we want to start doing any kind of material science. Okay, first we got this cyclobutane rings, giving it a very good rigidity of the monomer. We got these benzene rings, giving it the performance. Okay, good, that's structural, but how about the functions? Okay, I see some carboxylic acid here, okay, that anionic group, and I also seen some of the ammonia group here, which is the cationic group, and I got the idea here that like it's a thing like the light bulb in the cartoon that you see, right? That I can actually create organic, inorganic composites of this, okay? And maybe I can help to expand the functions of the polymers. So here are my aim and my objectives to create the modified of biopolyamides and biopolyimide that coming from the glucose just now. Okay, I'm going to go through this. Here are my strategies. We're going to talk about this in detail later, so I'm not worried about talking about this in detail right now, but let's go to chapter 2, which is the first polymers that I made, okay, biopolyamide as an ion exchanger. Now, let's talk about environment a little bit, because we got this toxic industrial waste going into the water every day. And the thing is, when the salt's going to the water, you see that it's always going to become the plus and the minus because of the high polarity of the water, right? So we got all these positive metal ions, which can be removed quite easily because we have a lot of anionic polymers. But how about these anions? Arsenate, chromate, iodate, iod, all these are actually in the ionic form. It's very hard to remove it from the water, okay? So I'm going to look at one in particular, which is the iodate and iodide. And this is going to be very connected to the one that the work that I do in Thailand. We will talk about one slide about the work that I do in Thailand. But the thing is, during the Fukushima disaster in Japan, if you can remember, 2011, there was an earthquake, there was a tsunami, and I understand that even in Indonesia, right, you also have like the problem of earthquake and tsunami. So in the future, if you want to make like a kind of nuclear power plants, and that's going to be very important, that the safetyness of it is the safety of it, right? So, but the problem is these iodine iodate are radioactive, and when it's going to the water, it's also have this iodine iodate form. And normally, how do you actually remove them? We use this conventional polystyrene based cation resin. You see, because we got this plus over here and minus over there, you can exchange the minus from, we can exchange iodide from the water, right? The problem with styrene base is that one, it have a very poor thermal properties. We talk about this later. Two, it have a very low biodegradability. This is styrene. Styrene is gonna take thousands of years to degrade, right? The thing is, it also depends on the petroleum-based resources. You need petroleum to make styrene. That's the problem. And that's why I wanted to bring in my sugar-derived polymers and trying to do something with it. As you can see, here is the glucose-based monomer. I'm going to try to quantize it and make it into another kind of monomer which have the positive ions on each side. And then I'm going to put in the diamines to create this polymers here, which I call the dication biopolyamide. And hopefully it's going to have excellent thermal and molecular properties. It can exchange inorganic anion like the iodide, and it can be worked in various conditions. Okay, so the next slide is going to tell me the methodologies that I have done. Basically, I just make monomer, I quaternize them. I use several methods to look at if the quaternized monomer is correctly quaternized, and then I make it into the polymers and use other kinds of methods to do this cationic BPA what is that called, characterizations, and then I do the iodide adsorption test. Now, normally in the adsorption test, I make the polymers, I put it in the water, right? I take it out of the water and I'm going to quantify how much iodide is left in the water. And the polymer itself will be categorized how it actually adsorbs iodide. And here is how I make the monomers. It's a very long process synthesis. Okay, days and night in the lab, and I actually came up with this quaternized 4,4-diaminotrosalic acid because the Q4ATA. This can be categorized by the mass spectrometry. If you actually, mass spectrum, sorry. If you know that the mass spectrum help you to know what is the mass of the things that you want to know, right? And M2 plus, because this one is cut into half. Normally, if it's a salt, it's do that in the mass spectrum. Okay, so calculated mass and the observed mass is pretty similar. So I'm quite confident that this Q4ATA is actually the one that I want. One more thing that I want to confirm is to use NMR. Okay, I use both high H NMR and C NMR, and you see that all the hydrogens and all the carbons come out pretty nicely in the chemical shift of the NMRs. Okay, and afterwards I'm going to make this into the polymers because this is just the monomer. Now here is the polymers, the monomers plus the diamines. I use 4 kinds of diamines here: R1, R2, R3, and R4. And you see that it connected the polycondensation reactions between the carboxylic acid and the amines, and that's giving me BPA, I'm sorry, I call it just PA R1, R2, R3, and R4 here according to its diamines. And the FTIR tell me that there are actually amide 1 and amide 2, so I got some kind of polymers in this. Okay, so that's going to be a lot of techniques that I'm being using, and that's just that. Okay, so if I hope you can remember, I hope all the students know all these techniques. If not, going to be confusing just a little bit. Next, I use a lot of techniques again to see how it's my polymers going to be looks like in terms of thermal properties, molecular characteristics. I use TPC, TGA, and DSC to see, and you can see that the TGA is quite good here, about 300 degrees Celsius for TD10. Okay, compared to Dalwex here. Okay, Dalwex is the conventional polystyrene resin that I talked about just now, which have a very low molecular weight. I mean, it have high molecular weight, but it have very low thermal properties and not degradables. Okay, so comparing to these Dalwex, we got a much higher thermal properties, and we also have about 95% use of renewable resources for PAR4 as well. This is not very necessary for me, but in one of the papers, I submitted this to the journal that they also asked us to calculate these column over here, and this is how we calculate it, okay? Now, this is just the molecular characteristics. Here, I have to convert the polymer into the hydroxide form. In order to do the hydroxide form, I just submerge it into KOH for 24 hours. And this is the commercialized form which we can use to remove iodide. Well, this can be used to remove radioactive iodide too, but for the sake of my study, I need to use OH minus so that I can study it pretty nicely, okay? So in order to study if this is already exchanged to this, okay, to prepare it, I use the SEM and EDX to see its structure and see if there is no iodide left in the contents, okay? Now, after this is QA treatments, we are ready to remove the iodide from the water. Now, after removing the iodide, just imagine I have already removing it. You see that the dosage that we use is about 5 grams per liter. The time it takes for it to remove this 10 milligram per liter iodide is about 120 minutes, okay? It takes quite a long time to remove it, but not that long, actually, it's only about 2 hours. And actually it's take about, it's going up to about 30 milligram per gram of efficiency. Okay, so hopefully everybody knows this efficiency removal and all this. I'm not going to talk about this, just going to show you how I actually study the adsorption, okay? And also with the adsorption, it's very frustrating that we have to learn about all these mathematics here. So let's not talk about mathematics, okay? Let's go on because I fit them to all these equations, first order, second order, Langmuir, Fondrich, or whatever. And yes, I got all the fittings. This is just telling me that what are the fittings of the polymers, what kind of adsorption mechanism is going to be using in the industry. So this is very important when you are working in the industry. So I'm going to move on to the next one, which is very, very important to discuss, which is the temperature. Now, when you work with radioactive substances, the water can get very, very hot, okay? And in this study, it can go up to 120 degrees Celsius. And they want the adsorption process to be working in 40 to about 93 degrees Celsius. And that's why I have to create the experiment that go up to about 90 degrees Celsius. And you see that all my biopolymers can actually sustain its iodide removal to the 100% and maybe removing to about 80% at 90 degrees Celsius. But the problem with the Dowex 550 is you see that it only works at about 40 to 50 degrees at maximum, and then it goes down very fast. So here, I'm going to say that maybe it's because of the biopolyamide have a very big molecular design. It have a very big how do I say that? It's have a very long chains. As you can see in my biopolymer study just now, that the molecular weight is quite high, okay? That's the first thing. And the polyamide itself has a very high water content by volume. And why high water content is very important because it acts like a barrier for the polystyrene or for the polymer degradation. So when in adsorption, sometimes you want polymer to be able to adsorb water when it do the adsorption, and this is the case that it needs, okay? With the water immersion test, we see that polyamide is better in water adsorption volume, and it can actually create a barrier to, because this OH can actually degrade this the chain right here. It can actually do the nucleophilic attack. So water barrier is very important. Molecular weight design is very important here. That's why in a higher temperature, my PA is a bit better than the polystyrene, okay? And also study about the pH variations from 2 to 12. It's quite good. At high pH, you want to have, you have OH minus more and more in the water. That's why it go down a little bit. But competitive ions here, we have the seawater here as well, that it can be used to about 40% in the seawater environment. And I did the regeneration cycle for 5 times. It can be used maybe 1 to 3 times. But the thing is, I only do 1 hour regenerations, I think. I can't remember the methodology exactly, but about 1 hour. But I think if you do more regenerations, maybe you can use it for more times, okay? So here is the biopolymer for iodide adsorption. I hope I'm not going too fast because we have one more polymer to talk about here. But I want to talk about the work in Thailand, which is my minor project in SIT here. It's a similar project, but here we use anthocyanin base. Okay, and I just discovered that because anthocyanin have O+ naturally, and it can actually bind to anions like iodide or chlorides. So it can be used for adsorption as well, okay? And when we talk about the Q, it might not be as good as the polyamide, but still it's quite good in using it as just a waste material for the adsorption, okay? So if you are interested, I actually published this already. You can also read about this paper. We use the computer generations example for this as well, okay? Now, here is the conclusion for these chapters. I created the polymer with the positive side, which is derived from the sugar, and I can actually remove things like radioactive iodide from the water, okay? And it can be working quite well. Now, the next one that I'm going to talk about, it's going to be another kind of polymer. It's a similar polymer coming from glucose as well, okay? Now, from polyamide, we're going to move on to biopolyimide. Now, biopolyimide, okay, we're going to use the metal hybrids and create a flame retardant thermostable organic film. In the industry today, okay, your phones, your buildings, your transportations, you need all these films, okay? And these films need to be flame retardant, okay? Because when there's a fire, so you can actually run away before it burned. Mechanical strength, of course, and we got the thermal degradation stability and optical transparency. Because this is the film, you need to be able to see through it. So transparency is very important, okay? So just now we were looking for adsorption properties. Right now we are looking for these properties. So how are we going to do this? How are we going to balance all these properties? Okay, this is the challenge here. We got some kind of metal alginate here, but it's not very flame retardant at all. Okay, we got the 2-carboxylethyl and the PLA2, but again, the heat release is quite good, but thermal degradation is very bad. So for here, I'm going to try to use the glucose base again for ACA to make biopolyimide. And it's going, because it have this carboxylic acid on each side, right? I'm going to do this complex of metal, okay? Scavenging to make it BPI metal complex here, okay? I didn't use the same thing as the one just now because we got this big molecular design here. It's not very good to use biopolyamide. So I use biopolyimide in this problem, okay? Now, so we're not going to use that. Okay, again, methodology overview, just going to skip this, but this is the film that I made, okay? I use 4-ACA. There's a lot of, I actually erased all these chemical properties, chemical synthesis. In my paper, it's actually going to have a detailed one. If you're interested, you can go and see. But you see that I created the COO minus here and exchanged this with the aluminum and copper, okay? And I see that this become organic inorganic composites because aluminum and copper have some flame retardancy property. So I just choose these metals. Okay, and here are the film. They are quite transparent, as you can see. This is the green one, the copper mate one, and this is the aluminum, which is quite transparent. Now, here is the absorbance from the wavelength. This is just a study if we have incorporated the metals in there and see what are the changes, okay? I also do local structure studies for exaph analysis and see that copper is actually incorporated very well. The problem is in Thailand, we don't have enough energy for aluminum. So sad that I didn't do this for aluminum, but for the exaph, hopefully I can do it in the future. Okay, so here just the copper, but the aluminum one is working very much better. Okay, we will see that later. Here is again mechanical properties, TGA, optical transparency, the thing that I want from my metals composites, right? The tensile strength here, quite good, 63.7 MPa. Not the best in the market out there, but it's good for some kind of film like this. We got TGA going up even to 400 degrees Celsius for BPI carboxylate aluminiums, and transparency is about 83%. It can be used as a film, I think, but maybe just a little bit cloudy, not 190 or something and above. So here is mechanical properties and optical properties here. Quite okay for me, okay, comparing to the other study right here. So not too bad. Then the things that are very important is the flame retardancy test, because when it's become the film and it's burned, you don't want it to drip into like a very hot molten things onto your body, right? And you don't want it to release so much energy. So we're going to use two tests to test for the flame retardancy. The one is UL94V and another one is microscale combustion calorimetry. Okay, this one is going to tell you what is the energy that's being released when you are using the when you are burning the polymers. UL94 is going to tell you, is there a dripping? Is that going to ignite into fire? I got the video here. Okay, this one actually going to show you when it's burned. Now, the first one I'm trying to do is polypropylene. This is the commercial live polypropylene. You see that's dripping there. That's not very good. That's a very bad transparent flame retardancy here. If you're standing there, you're going to be dripped by very hot things here. Okay, this is the first form of BPI potassium. It's burning right away. It's not very good as well because it doesn't sustain its structure. You can see that. Okay, this is not so good. Now, when we bring in the copper BPI, you see that when it burned, it sustained itself a little, okay, before it starts to ignite again. Okay, we will talk about this, why it's happened this way, okay, and it has some glowing there as well. But here is actually the best aluminum. You see that when the fire is burning, the aluminum protecting the layer of the polymer, and it's not really burning that fast. So here it's going to be the BPI CaO aluminum. This is the very best in this series. Okay, so I'm going to tell you that the first biopoly image is failed. The potassium one not very good. There's no dripping or cotton ignitions, but for the aluminum is actually sustaining very good. It has 1 and 0 for the rating. V0 is actually the best rating for this. Okay. Now, we also look at how it's actually release energy when it's burned, because you know that if it releases so much energy and it burned and you are in the building, you can feel it's very, very hot in the building, and that's not very good. It can kill you and all this if it's getting too hot when it's burned. So you can see that the aluminum has a very low total energy release and all this. Okay, so we want the value to be as low as possible. You see all the commercial based one. I mean the other studies they are also quite low in a 6, 7, but for our aluminum part we only have 4.5 total heat release, which is very, very low, which is quite good for the flame retardancy property. Okay. Now we always study chemistry, right? And we want to know why this is good and why these are not so good, the copper one, the potassium one, and all these. And there are a way to study that. Okay, so we study Raman shift. Okay, we're going to look at its peaks, and we're going to see the D and G peak and do the ratio of them. Okay, the higher the ratio is going to tell me that the higher the graphite char is going to be there. If it's a higher ratio, it means that there are more smaller microcrystallized size. That means that the burning is very slow. And we can look at this in the SEM as well. You see that aluminum has a very small particles there. And we have to compare it to the CaOK, the normal potassium kind, which have a very big hole, which is telling me that that's burning very fast. And these two are burning much slower than this one, okay? And we also do this flame retardance mechanism using the XPS, right? Yeah, here it's XPS. You can see that we got char residues which have the aluminum oxide and aluminum hydroxide here. It's just telling me the mechanisms of when you burn this, you're going to have this big layer and the water will be coming out according to the formulas, okay? And that's why it's a very, very good flame retardancy here because of the water. For the copper type, you see that it's sustained for a while and then it starts to burn very fast. And there are some glowing, and I think it's because of this oxygen here that's coming out from this here. That's why, if you remember in the video for the copper, the blue-green film, you got oxygen there. That's why it starts to glow. Okay, so here is also the flame retardancy test for me. And in conclusions, I want to say that I created a glucose-based polymer with composites of aluminum and copper. It's quite transparent. It can be burned and sustain its structure for a while, especially these aluminum types, okay? And using all the Raman, XPS, and all these, I can study the flame retardancy of this film here. Okay, now that's the second polymers composites. Okay, the last one here is pretty new. Okay, I can't show much information because it's not really published yet, but it's going to be a lanthanide ions composite as photoluminescent sensor. Okay, the first one is the iodide absorption. Second one, I do flame retardance. Now let's see something glow in color. Okay, because it's photoluminescence. Now, if you study luminescence before, you're going to come across this called volatile organic compound sensors. Why is it sensor? Why VOC is very dangerous for our health? It's because if you breathe a lot of VOCs, right, you're gonna get asthma attacks, nauseous, and all this. So when you are in the room like me here, you want to see how much VOCs in the room, you're gonna have some kind of sensors, okay? You can have calorimetric sensor, you can have surface acoustic wave, but one thing that's particularly give me the attention is photoluminescent sensors, okay? The advantage is you don't have to have a direct electrical contacts and it gives you real-time information, okay? But the thing is, it's only limited to the MOFs, which is the metal organic frameworks. And if you remember my study, my polymer is not really an NOF, right? So I'm going to try to create something that it's not really created before. So it's working similar to MOF. Okay, so I'm going to give the lanthanides the attention here. The lanthanide ions are those in the last sections of the chemical tables. If you remember the lanthanides here until this, I'm going to put the lanthanides into the ligands. My ligands here is the polymers that I made. And hopefully this is going to help me to work as a VOC sensor. Okay, so if we have the ligands, if there are some VOCs, it's going to help me. Okay, now the lanthanide itself, it's already fluorescence. Okay, if you look at europium or terbium in particular, they are very, very fluorescent. You see that europium gives you the visible light of orange red light, and terbium gives you a visible light of green light, and this is due to a level of this energy here. It's the basic chemistry here, so I'm not going to talk about that, but you can see that they are already fluorescent by itself. But the thing is, okay, I'm going to create that. It's very big gap of energy. That's why you got a very, very high, very bright lights, okay? This is methodologies here. Here you see that europiums, europium chlorides and terbium chloride under the UV ray of 320, you already see the bright lights here, okay? And here is the polymers that I use, again, BPI. Under UV, it creates this kind of blue color. Normally, benzene, I think it's because of the benzene rings here, okay? The benzene rings, you can see this thing here. Yeah, benzene normally absorbs these two and creating these blue lights over here. But for the europium, we're going to give it about 550 nanometers and about 550 nanometers for the terbium as well. And that's why, but problem is these salts it's already bright. Then why I want to mix it with the polymers, okay? You will see that after mixing it with the polymers, okay, I'm creating this it's not very like nice polymer yet because it's still working. It's a very wriggling polymers. But you see, the polymers actually have a much brighter lights. Okay, when you actually put it in the polymers, it's called the quenching effects. The quenching effect will create a brighter fluorescence light when you add some kind of ligands into the lantanides. Okay, so the lantanide itself, it's not so bright, but then when you put in the ligands like the polymers over here, you create a much brighter photoluminescence, and it can also be used in the sensor. So now I'll be testing for the sensor. Okay, so by testing the sensor, it's very easy. Okay, this is just explanation why it's become brighter and all this. You can see that here it's the BPI europiums, and here it's just europium chloride. You see that when I add in the ligand, the brightness is going up much higher. Okay, there are some explanations to that. I'm not sure 100% because I'm not really understand why it's doing this. So it's still under study. So I'm just going to tell you that it's actually going much brighter. The same thing happened in the terbium. When I add in the ligand, you see that the brightness of the photoluminescence is much higher, which is much better just using the ligand and using the lantanide itself. Okay, it might be because this is called a quenching effect. I'm going to test it for VOCs now. Okay, this is how I try to explain it. I don't know if I want to explain it here, but it's just a system called the S1T1, and then it's going to this intermolecular and energy absorption and all these things. Yeah. So, okay, I'm going to Dexter electron transfer and Foster mechanism. It's kind of interesting, but if I have to explain this in terms of physics, chemistry, it's going to take a very long time. So let's skip to a more interesting thing, which the VOC sensor. Okay. Now, how I do it is just clips the tapes here. This is the BPI EU, and then I'm going to put the solvent here. All the solvent I use are acetone, ethanol, ethyl acetate, and so on, metal, and then free just a water. Okay, and you see that this VOC will just evaporate and touch on the film. And then I'm going to put it under the DI. I'm going to put it under the UV. You will see that when it have acetone, the brightness of this going down. And then when I wash it with DI water and then do the same test again, the brightness go up. You see that this can be used as a sensor. If there is an acetones, then you have the brightness going down. If there is no acetone, then the brightness going up. Okay, so if you're going to integrate this into the some kind of machines, you can actually come out with a number like higher acetone is going down, the dimness going down, the number will go down. Okay, we haven't go through until that kind of technology yet because this is just the first thing we are knowing, but it can use to quench acetones. Okay, and I haven't tried the others, but hopefully the others will create the same effects of with VOCs, the brightness going down, and with the DI, the brightness going up to the maximum again. Okay, so here is the VOC sensors. And I have to say that the sensitivity of quenching is very important here, okay, because it can sense 0.05% acetones, and it can sense like different kind of percent of acetones here. So it depends on the sensitivity. As the acetone go up, this intensity go down, as I say, okay, and this is trying to explain the sensitivity in the acetone here. Okay, now as I said that we created a photoluminescence BPI, okay, with the europiums and with terbiums, and with the ligands, okay, with the ligands here, when you have the UV, it's going to transfer the energy into lantanide. It's going to give a very big emissions. But with acetones, the acetone will quench it, and it will not, sorry, the acetone will just block it, and it cannot transfer the energy. That's why you have a quenched emission here. So here is the mechanism that I'm trying to explain right here. And hopefully it's in the next study, I can actually do much more. I'm trying to do XR for this too, and hopefully it's going to come out with a very good study. Okay. Now, in conclusions, I have created 3 kinds of biopolymers composites. Okay, the first one is for the absorption of iodide. The next one is for the burning of flame retardancy, and the last one is for the photoluminescence as a sensor for VOC. Okay, so this is organic inorganic composite developments that I have to explain here. Hopefully I can explain things. It's quite fast, I know, but I want to show every technology that I have done. Okay, and to thanks you all, I showing you this sakura trees in Jai during spring. Sakura only come out in spring for 1 week. So if that 1 week is raining, then you won't see it. It's not gonna be so bad, but this is a very nice sunny day at that time that I took this picture. Okay, so I want to thank everybody here, and thank you University of Jammu, and thank you Hankara for inviting me for this lecture. And if you have any questions, I'm going to take it right now. Thank you so much.
Okay, thank you very much, Dr. Jakapon, for your very nice important talk today. As presented before, Dr. Jakapon and his research team have successfully synthesized the anthocyanin-based adsorbent for radioactive iodine remediation from various kinds of biomass waste, with surely effective and efficient processing. Okay, as we know in his presentation also, Dr. Jakapon and his team also have developed a flame retardant transparent film with high optical transparency from the amino acid-based polyamide PPI for electric devices and building materials. Okay, now we come to the discussion section for questions. Ladies and gentlemen, you can also ask Dr. Jakapon directly with raised hand. Yeah, Dr. Jakapon, before I read some question from the audience, actually I'm interested with your presentation about utilization of anthocyanin.
Yes.
But maybe it is a basic question. Yeah.
Mm-hmm.
You said in your presentation that anthocyanin have gathered the attention of scientific community mostly due to their wide range of possible application. My question is, compared to other application, what are your consideration for using anthocyanin for wastewater treatment?
Okay. Actually, it's if we use the anthocyanin base, so mangosteen peels and onion peels and all these, right?
Yeah.
Yes, it can be. I think it can be used, but quite a limited applications though, because I didn't talk explicitly about that. But in my paper, you can see that at high temperature, for example, it is not working very well. So so I think it cannot be used in a real industry standard. I think it can work in the environmental real environment, because it's actually working quite nice in the seawater or river water. Seawater, not so good, but river water, groundwater can be worked quite well. So, but in the industry where the temperature is very high, anthocyanin cannot really be used that much because it degrades very fast. Yes, that's the problems.
Okay.
Yeah, but if you can actually create like some kind of adsorbent that integrate anthocyanin in there, you can try to do it as well. Yeah.
Okay, thank you. Nice knowledge. Okay, anyone maybe want to directly ask question to Dr. Jakapon? This Hanggaras Derajat, Dr. Hanggaras Derajat, please.
Okay, sorry. Okay, thank you very much, Dr. Maksum. I hope you hear my voice.
Yes.
Yeah. Hello, Chad. How are you? So actually, Dr. Jakapon is one of our collaborator. Okay. Anyway, nice for your thank for your nice talk. So I have 2 questions, 2 simple questions actually. So first is, when we consider about your um, your bioabsorbent, bioabsorbent. For example, you want to, for example, I want to use your biosorbent or your absorbent to remove a series of anions, pollutants. I mean, so my question is how to tune the selectivity of your absorbent. For instance, if we consider the anions pollutant, of course we know about the arsenate, arsenic with pentavalent oxidation state. So can I tune the selectivity, or let's say the preferential absorption affinity to specific anions? This is the first question. The second one is I'm interested about the your I forget, so carboxylate copper or something, yeah. Sorry. So actually my question is there any possibility that for instance, the copper ions change its oxidation state during the processing or during the use? Because the copper is quite easy to be altered or to be changed in the of its oxidation state. So I just worry that the oxidation state may change, or because this is a transition metals. Okay.
Yeah, I can understand.
Thank you.
Okay, for the first questions, right? Selectivity. I think it's always going to, selectivity is very important for absorptions. For example, you talk about arsenate, right? Actually, I tried arsenate before. Even normal resins cannot really remove arsenate from the water. I don't know. It might be because of the when we select selectivity, right? We look at the anions. Like for example, iodide. It's just I understand it's big, but it's just one ion. Arsenate is like ASO or something. It's quite a clumps of a lot of. It's like a molecules, right?
Yeah,
clumps of like atoms together. So I can understand because of the structure like that. It's very hard to remove for arsenate. Okay, so when you talk about selectivity, you have to look at the strength of the plus and minus. Yeah, the strength of the electrostatic stativity. I think that's the word, right? And then and I think for arsenate it's very low compared when we when we put it next to things like quaternary amines. Yeah, so that's why it's not a very good selectivity for things like arsenate or chromate, which is a very clumsy and big ions compared to just iodide fluoride. So, but for those, if you can try just a physical absorptions, it's maybe more possible, I think. What do you think? Because physical absorption, you only use the size of the pores and then you just blocked it. Maybe it's a bit more feasible to remove that kind of big ions. But small ions, you can use that for selectivity tests like I did for iodide, fluoride, and all these. But for big ions, I think try for physical absorptions, I think it's a bit easier, like or even a membrane or something like that. Might be more feasible, I think. Yeah. But
okay. Yeah, thank you. So following your answer, so let's say if I want to develop your materials for, let's say, industry or something, is this possible? I mean, considering the economic consideration, or
yes, for the industry, right? The most difficult part is not the one that I do. The most difficult part is the one that Kaneko Sensei have been doing, is the making of the monomer from glucose. So that's the most expensive part. And because of the bacterial fermentation, it's still taking a long time. It's still taking a very expensive route. I think right now he's trying to develop that into industry to like cut down chemicals, to make some, maybe he's changing like bacterial colonies, make it easier. So he's doing a lot of things to adapt it into the industries. So I think my part is a bit, if his part is successful, then my part is not that difficult at all. So we have just to wait for that. Yes.
Okay, thank you, thank you.
And then the second question is about copper, right? So you are I think you are worried about the copper toxicity or something like that, is it?
And I'm not that sure, but I mean the copper oxidation state of the copper, of course, is copper exists not only in one oxidation state, right? So my question is, during the use or even the processing of your material that involve copper, so is any possibility that the oxidation state of the copper changes, or I mean the
actually, okay, let me see. I think it's actually changed. Let me go back to that. I think I showed the XPS there, right? Yeah, here. From the XPS itself.
okay, yeah.
Yeah, it's actually yes, it's actually changed. Here is changed to Cu2, so it's changed to a crystalline structure more than the CuO form. So actually, this is more like a char layer, Cu2O. But the problem here is the oxygen that come out with it. If you can see from the I haven't done the gas chromatography of this, and I can't be sure that oxygen really there. But from the XPS, I can derive it to be like this. So it just
Okay.
It just might.
I didn't see this one. So actually, the oxidation state of copper reduced from 1 to from 2 to 1. Okay, thank you.
Thank you.
Thank you, Dr. Hanggaras Richard, for next question. Now, please allow me to read some question from participant of this class. There are 3 questions. Please commit to share in screen. Sorry, Dr. Jakapon, could you help me to stop share first? Oh. Wait. Sorry. For the host, please make Bu Bekti Palupi. Oh, Bu Meta, yeah. Thank you. Okay, first question from Pawan Suryanto from IPB, Institut Pertanian Bogor University. Dr. Jakapon, when we talked about biomass, we only must consider the heterogeneity of raw material to use. So how to control the chemical and physical properties of raw material to get proper reproducibility of them?
This is a very hard things to do, okay?
Yeah.
Yes. In your study, I don't know how to, okay, in your study, trying to use this, what I can say is you have to try to use the same batch of material. Okay, for example, I'm using mangosteen, okay, or onion peels study. I'm trying to get the mangosteen as much as possible at that time and then just stick with that. Because if you go to a different market, different farms, mangosteen have different kind of, there are many different kinds of mangosteen and many different kinds of anthocyanin in different mangosteens too. So from what I can say is you just need to try to control your batch, try to preserve it and use that until your project is finished. Okay, so just to control it, I understand that chemical and physical properties can change, and that's the thing you need to study. That's why if you like look at it's not a problem with my material for biopolymers because those are already made biopolymers. So glucose into the monomer. The monomer is quite controlled by itself. But things like mangosteen, or if you use whatever durian, for example, yes, difficult. So that's why you need to study into it chemical and physical properties too. For me, I study how anthocyanin contents affects the iodide absorptions, okay? And that contents can tell me, okay, let's say you get a new raw materials, how much is the anthocyanin in there and how it's going to affect the absorption. So you need to study into that. And the first study is very important for you to control the batch experiment. Okay, so all I can say is that when you know the chemical and physical property that affects your raw materials, whenever new raw materials come in, you can just test for those properties and you can use it accordingly. That's all I can say. The first batch is the hardest for this, I think. Yeah.
Yeah.
I hope I can answer the question. Thank you.
Okay, thank you. Maybe there is feedback from Pak Wawan for the question.
What are the criteria to confirm that our polymers are really biodegradable? Okay, there are a lot of tests for that. Okay, easiest test is biodegradable. It means that it degrades by itself. You can try, the harder one is to use these bacteria tests. You can use, there's a lot of tests for this as well. You can actually just put the materials, for example, plastics, right, into a bacteria batch, and then you just measure the gas that come out. That's one thing to test. You can put it under the earth. You can put it in the environment that you simulate, and you can see how it disappear and taste the environment. If it have, like, for example, plastics, microplastics, very important, right? So let's say you are trying to degrade under the water, you have to see like what kind of things in the water. That is there any microplastic in the water, for example, in the soil, you know? So the easiest way, just put UV light on it like a sun and see if it actually reduce in size or anything like that. Yeah, but that's the easiest way to do biodegradability. But there's many work that can be done for biodegradability. You can do it in the real life earth, you know, the under the ground or whatever, or you can simulate the conditions for it as well. Maybe simulating is much better, I think. Yeah, but you can do a lot of things for that. Yeah.
Okay, thank you. Next question, please. From FE Nadila Kiandita, is one of student in undergraduate chemical engineering department. Can BPA biopolymer only be used for anion exchange, especially iodide anion? Is there a biopolymer that can be used for anion exchange in general, or is it only a specific biopolymer for certain anion exchange?
No, this is not the only specific biopolymer. There are many, any polymer that you can synthesize it. I see some people use, what is that called? The chitosanes as well. That's another great biopolymer, but the only I can only say biopolyamide that I use, BPA. It's the polymer that has a very high mechanical properties and can be used in the higher temperatures. Okay, there are many other kinds of biopolymers as well. There's a lot of work in chitosanes that they create like positive charges. Chitosan itself is already positive, has a lot of ammonium in there. So yes, there are many other biopolymers, but my own polymer, I use it for the mechanical and thermal properties. That's why I need to use BPA for this environment, because iodine, it's radioactive iodine is very hot when you work in the environment, in the real industry. So I need to use this BPA due to its being able to absorb iodide in the high temperature conditions. Yeah, but yes, there are many other biopolymers that can do that.
Okay. Thank you, Dr. Jakapon. Unfortunately, this is the last question, and we have come to the end of this first section. Again, thank you very much, Dr. Jakapon, for a great knowledge. Ladies and gentlemen, please give a virtual applause to Dr. Jakapon for his outstanding presentation.
Thank you.
Okay, thank you. Oh, okay. Sorry. Our next speaker is Dr. Rizky Fitria Darmayanti. It is now my pleasure to introduce our second lecturer. Please, Bu Meta or Bu Bekti, to share the CV of our second speaker. Okay. As seen in your screen, ladies and gentlemen, Dr. Rizky Fitria Darmayanti obtained her PhD at Department of Bioscience and Biotechnology of Kyushu University, Kyudai, in Japan under Professor Kenji Tsunomoto. She is currently a lecturer of bioprocess engineering at the Chemical Engineering Department of University of Jember. Her main research interests in renewable energy and waste utilization. Yeah, her current research activity are in the field of lignocellulosic material for biofuel production and the development of novel fermentation for biobutanol production. Ladies and gentlemen, would you please welcome Dr. Rizky Fitria Darmayanti. Dr. Rizky?
Hello, could you hear my voice?
Yes, it's clear. It's clear.
Okay, thank you very much.
Time and screen is yours.
Okay, thank you very much. Firstly, could anyone help me to allow me to share my screen? I'm sorry. Okay, let me start first. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Thank you very much, Dr. Maktoum, for the introduction. And let me introduce myself once again. Maybe here I want to talk about our research about bioenergy, especially in the integrated recovery for okay, thank you very much, the committee, for allowing me to start my screen. Okay, my name is Rizky Fitria Darmayanti. I'm from the Research Center Based Chemical Products in the Department of Chemical Engineering, University of Jember. Okay, as we know that biomass in this world is very abundant, and the cost of this feedstock is very low. So hopefully with this abundance, we can make some sustainable solution for our future. Using fermentation, we can produce such as sugars from lignocellulosic biomass, energy, materials, and other chemicals, many types of chemicals. And why do we choose fermentation? Comparing with high pressure and high temperature, some thermochemicals process, because we can convert this low cost biomass into these valuable products with lower energy and higher selectivity, because we use microorganism. Of course, is the recyclability of the biocatalyst itself. The biocatalyst we mean here is the microorganism. Yeah. Then what is the integrated recovery? If we have some feedstock, we can say have some biomass, and then we degrade it to lignin or some sugars. We can ferment the stock to some products. Then usually this fermentation will release some gases. And of course, the product, the product that we desire to harvest. Then we do separation. But after that, we recycle. We recycle some media, the nutrient, and some the remaining substrate, so we can use it again here for fermentation. We can use it and we can consume it more efficiently. Then the more concentrated product will be purified until the high quality product standard is reached. Using this recovery, we could reduce the toxic product concentration in the nutrient. And because we reduce the toxic product, we give some more conducive environment for the microorganism, so they could grow better and give them higher activity, higher productivity, so they could give more product for us. Then, of course, as we know in the industry, separation used to consume a lot of energy. Most of the energy is in the separation process. So by using the integrated recovery, we could harvest the product with lower energy. For fermentation, usually we use it for increasing the productivity in some fermentations, such as butanol production, biohydrogen production, methane or biogas, some organic acids, and surfactant. They are all some toxic metabolites, toxic metabolites for microorganisms that they produce. And after some limits of concentration, the bacteria started to die. That's why we need to separate the product simultaneously in the media. So what kind of integrated separation is suitable for our desired process or products? We can make some consideration based on the cost, because the minimal energy and material cost to maintain favorable energetic and economic yields is necessary. And biocompatibility. We want to reduce the toxicity concentration of the products in the media, so the separation itself must be biocompatible. It should maintain the microbial activity and should not be adversely impacted the viability of the microorganism. Then it must be selective to our desired product. In fermentation, we know that there are some intermediates, Maybe if we separate this intermediate, Also, it will reduce the productivity because the intermediate is lost, yeah. So it must be selective, more separating the products than others. We could make it from some properties like affinity or molecular size, and yeah, it depends on our product. And then how about the regeneration of the separating agents, such as maybe in extraction we have solvent, in absorption we have adsorbent. The full regeneration must be possible with minimum energy and enabling both vessel release of recovered product and the reuse of materials. So we can reuse, yeah, the materials for separation easily with economic feasible process. Then how about the robustness of the separation? It must be resistant against non-ideal interaction with medium or cells, minimizing some process due to inhibition, biofouling, degradation, and polarization. And how about the modularity of the process? It must be how to say some kind of flexible, yeah, flexible and easy to be compatible with some modification in the process. So this all factor must be considered when we use integrated separation for fermentation. We will discuss example. First, I would like to discuss about biohydrogen. There are some factors affecting biohydrogen production. In biohydrogen production, usually we could choose some fermenter, and then some acid will be produced, yeah, during fermentation simultaneously with the hydrogen gas and carbon dioxide. So the gas we usually harvest from the headspace of the fermenter. Then we can use it. We have to separate it from carbon dioxide first, and then we have to maintain, yeah, the mass transfer in this area from the liquid to gas. So we could obtain the product here optimally and maintain the productivity of the biohydrogen itself in the media. Yeah, for example, actually the hydrogen solubility in the water is not high. It's only about 0.0016 gram hydrogen per kilogram water in the normal condition, yeah. But what is the problem then? So we have to do the integrated separation, because sometimes when hydrogen production exceeds hydrogen mass transfer from liquid to gas, I mean the rate, yeah, the rate of the mass transfer is lower than the production of hydrogen, very high production of hydrogen. We could experience some super saturation in the media, yeah, in the liquid media. Then if it occurs, of course it will disturb and kill, some bacteria in the fermenter. That's why we have to maintain. There are some scheme of a gas recycling here. We can use the conventional one without separation. Yeah, we use the gas spurging. After some pressure here increase, we recycle the gas to enhance the mass transfers from liquid to gas. But here, there are some addition like membrane, so the hydrogen and carbon dioxide will be separated. We harvest the hydrogen and the carbon dioxide rich gas, we sparge to the fermenter. By using this, the concentration of hydrogen in the media will be significantly reduced. Then how about the membrane characteristic? It will determine the productivity and the efficiency of the process, of course. Moderator, please remind me if it will be over soon, yeah? Okay. There are. Thank you very much, the moderator. He is my husband.
You're welcome.
This is permeability, which depends on the flux of gas, pressure, and the thickness of the membrane. And this is the permeability. Then this is the selectivity of the membrane. If we compare the permeability of the component 1 and 2, for example, carbon dioxide and hydrogen, we can get the selectivity. Here is the reaction for biohydrogen fermentation. We ferment some sugar hydrolyzed with bacteria, then we can get some organic acid, carbon dioxide, and hydrogen. In the gas phase, we have carbon dioxide and hydrogens. And the selectivity depends on the type of penetrants. We have the penetrants here, carbon dioxide and hydrogen. The chemical composition, structure, and the morphology of the membrane, and also the configuration of the membrane modules. Maybe we have some hollow fiber or some spiral wound or other configuration, yeah. It will affect the selectivity. Then this is some example of the membrane that we can use for the biohydrogen harvesting, yeah. We have cellulose acetate, polyamide, ethyl cellulose, and PBAX. We have here, if the selectivity of CO2 compared to hydrogen is lower than 1, so this is the hydrogen selective. It means that hydrogen will penetrate the membrane, then the permeate, the permeate is hydrogen rich. And this membrane, if we use it, the selectivity is more than 1 for CO2 compared to hydrogen. It means that carbon dioxide will be more concentrated in the permeate than in retentate. This is the performance of the biohydrogen fermentation using gas separation membrane. We could see here that the productivity, yeah, here we have the productivity is stable, yeah, stable, not so significantly fluctuating during the fermentation. From the hydrogen fermentation, of course, we can use the hydrogen for the energy production. And how about the carbon dioxide? After we separate using membrane, we can use it also, the carbon dioxide rich gas for algae cultivation, especially, yeah. So this is a very promising, yeah, promising process. And then this is also methane separation from fermentation. If we know that methanogenic bacteria can consume the substrate from fermentation. Firstly, the fermentation will produce acid, and then the acid will be converted to methane. If we use mixed bacteria and substrate, the substrate is the raw material, vegetable waste. In this case, the media will be saturated with acid. This inhibit the methane production in fermentation, because the conversion of the vegetable waste itself is very fast comparing with the methanogenic bacterial growth. So we can make it separated like this. Here, the vegetable waste conversion from cellulose to acid. Then we pump them to another reactor. So the acid will be converted by the methanogenic bacteria. Then we pump again here. What is the purpose of recycling the bacteria? Not the bacteria, I mean the media, yeah, is to diluting the acid from this process. So the substrate will be converted continuously. Here, vegetable converted to acid, and then here, vegetable acid is converted to methane. We can see using the doubler, the methane production is higher, and if we increase the inoculum to substrate ratio, we could also improve the production. Using the double reactor, we could reach about 400 milliliter per gram. And also this is the dissolved organic carbon. Using the double reactor, the carbon or the feedstock, the material in the media is consumed more effectively. Only some small amount of remaining substrate. There's also another technology for separation for biogas using biochar. We can use it also. And how this works? This biochar, if we add in biogas fermenter, it will help to how to say, absorb some inhibitors, and then improving the enzyme activity. Besides hydrogen and methane as bioenergy from fermentation, also there are some integrated separation for other fermentation like organic acid. We have like lactic acid, which is now we use for lactic acid products. We could use it for resins, textile, printing, and adhesive. This is the kind of biopolymer. So, what is the problem using the conventional lactic acid separation? Usually, the lactic acid is precipitated to become lactate, But the cost of this process is almost 50% of the total production cost, and generates a large amount of solid waste. That's why some more efficient integrated separation is developed. In the media of lactic acid, the concentration reached around 54,000 ppm. It is inhibiting the lactic acid production by the bacteria. This is some integrated separation for lactic acid. There are active fermentation, aqueous to phase separation, electrodialysis, and absorption. And also there is the surfactant process, by fermentation, such as lipids. So, what is the problem, using in the production of surfactant? Especially, there are some foaming when we don't separate the product simultaneously. There will be foam, and it will disturb the mass transfer from the substrate to bacteria. Also, there is the viscous phase of surfactant. It also makes some distance between bacteria and the substrate. There are some separation technique that we can use, such as solvent extraction, absorption, membrane, and from foam fractionation. These are the products which is suitable for this separation. Here we can see that the biosurfactant production is increasing using the integrated separation. Okay, then we will discuss, we will talk about the research of our department. It is the utilization of cocoa pod husk for biobutanol production with zero waste concept. Firstly, I want to introduce biobutanol to us. Maybe some of us are very familiar with ethanol, but not butanol. Butanol, as we know, is the alcohol with 4 carbons. Mainly, we made it by oxo process from propane gas. This butanol is now currently used for the feedstock for some products. Here we can see some butyl acrylate, butyl acetate, and others. And this is the products that we use in our daily life. Yeah. So it is a very important platform chemicals. Besides being used for the feedstock for chemicals, biobutanol can be used as the gasoline substitute. Here we could see the comparison of the properties between ethanol and butanol to gasoline. The octane number, the vapor pressure also, it is closer, yeah, to gasoline, more similar to gasoline. Also, the heating value is higher than ethanol, and the most important is it's not corrosive, so we can use it in our engine, without modification. Blending up to of butanol up to 40% with a gasoline can improve the engine performance. Butanol we can produce, yeah, from glucose with this metabolic pathway. Usually we use Clostridium bacteria. There are some species we can use to produce butanol. Simply, the glucose is converted, yeah, to acetate, then butyrate also. This acetate is converted to ethanol and acetone, then the butyrate is converted to butanol. So the final product of this fermentation is butanol, acetone, and ethanol. And this is the intermediate, this acetic acid and butyric acid. And as we know, these products are toxic, yeah, to the bacteria. So after some limitation, 20 gram per liter, maybe the bacteria will die. This is our roadmap for our research. In the first year, we did the characterization, then separate the pectin, do delignification, hydrolysis, fermentation, then adding the product to fuel grade, then test the product in the combustion engine, then scale up the process. So we could produce the butanol in efficient process, yeah. This is our first year research. In our city, in Jember, and also maybe in Indonesia, we have a lot of agricultural products, and here we can see some waste of the product, such as tobacco stem, cocoa pod husk, sugarcane bagasse, rice straw, cassava peel, and coffee ground. They are a very abundant resources, yeah, in our country. They all have cellulose and hemicellulose, and the portion of the waste is quite high. And this is the morphology of the agricultural waste. After characterizing the agricultural waste, we see some potential, yeah, here from cocoa potash. They have high amount of pectin. We can use it for, how to say, medicine, yeah, medicine and food product, and it is very valuable. And the waste portion of the cocoa potash reach 70%, yeah. Also, we can make some bioplastic fuels and chemicals platform from all of this lignocellulosic biomass. Because of the high pectin composition here, we selected cocoa potash as the feedstock for our research. This is the process of converting the biomass. We have to degrade the lignin using the lignification, then hydrolyze the cellulose and hemicellulose, and then convert the sugars by fermentation. And also, after that, we can get butanol, then separate it for high concentrated product. Now, this is the pectin that we obtain from the cocoa potash. We use ultrasonation method, and here we can see that around 10%, yeah, 10% yield of the pectin. 10% out of 12%, yeah, pectin composition in the cocoa potash. This is the wet pectin and this is the dry pectin. We use ultrasonation. This is a low temperature, yeah, low temperature process. Then after that, the remaining solid of the extracted cocoa potash, we did the delignification process using microwave pretreatment with alkali. And here we can see that the optimum value for sample to solvent ratio is 0.025 and irradiation time of 2.5 minutes. Lignin was decreased significantly from 21 to around 2%. This is the cocoa potash after the lignification. And after that, before we started the fermentation, in the fermentation itself, we have some refresh process, yeah, refresh process for the bacteria after storage. Here, we explore some potential in Indonesia because we have a lot of type of starch, yeah, in Indonesia. We try to find which one is the best for the refresh for the Clostridium saccharoperbutyl acetonidium N14. And here we can see that the sweet corn resulted in the highest butanol concentration. So we use this sweet corn for the refresh, only small amount. But for the main fermentation, we use the lignocellulosic biomass. And then we did the extractive fermentation with large extractant volume. Here in the media, in the aqueous phase, there is sugar converted to the solvent. and then the butanol is recovered by the extractant. Why did we use extraction for the biobutanol recovery? Because it consumes small amount of energy compared with others for biobutanol separation. We use the large ratio of extractant to growth to decrease the volume of media, because media contain nutrient which is very costly. Here for the biocompatible extractant, we have to choose the biocompatible, which is not killing the bacteria. We have the distribution coefficient for acetone and butanol here. We combine both of them. Allyl alcohol here, extracted butanol in about 3.1 distribution coefficient. And 3-butyrene, it is not frequently used, but we try to use to extract the acetone as well. And this is the result. We also use immobilized cells to protect the cells inside from the toxic environment containing butanol and also acetone and ethanol. Here, this is the conventional process with extraction, normal extraction, with low ratio of extractant to medium. And this is the extractive fat batch fermentation with large extractant volume and immobilized cell. Here we can see that the total butanol produced is 4 times higher. So we try to use this for the biobutanol production. This is the flow diagram of the process. We try to analyze the energy and also economical aspect of this process. This is for the delignification and also hydrolysis. And this is the extractive fermentation. So the extractant, we mix it in the fermenter. We just separate it in the decanter here. So they will separate to 2 phases of extractant and the aqueous phase. Then the extractant, because the extractant and butanol has quite far difference of temperature, boiling temperature. So it will result in the more concentrated product. Then when we have to distillate the butanol in water, we have some azeotrope also, so it will be an obstacle for distillation to get the high concentrated product. And then this is the last distillation. This is the mass balance of the process in fermentation, and this is in the distillation. We use the simulation using Aspen Plus. We get this number. From here, we can get the butanol and acetone in high purity, 99, above 99%, because of no azeotropic mixture. So after we calculated the utility, we can get the energy requirement for this 41.3 megajoule per kilogram acetone and butanol. If we compare with other process, this is oxosynthesis, the conventional process. This is the fermentation, conventional fermentation, yeah. The energy is much lower. But from the cost, because we have some like chemicals, yeah, chemicals for more chemicals in the production, like enzyme. So some production cost was a little bit higher. Then we have to optimize again, yeah, this process, so we could meet the competitive price. The conclusion of this research is that integrated recovery of biobutanol increased the concentration and productivity by reducing the toxicity of the product in media. Immobilization also protected cells from toxic environment, including toxic metabolites and inhibitors. Inhibitors here from some other process like peripheral, yeah? And this process is economically competitive, but needs some optimization to reach the market price. That's all about this research. And I would like also introduce the personnel in our research center. We have Dr. Boy Arif. He has research in bioactive compound extraction, biopolymer, and bioplatform chemicals. Also, we have Mrs. Dita with solvent-free essential oil extraction, Mrs. Istiqomah in membrane DSSC, and Mrs. Ari Susanti in biodegradable plastic, Mrs. Bhakti in bioethanol, and Mrs. Mehta in adsorbent. And this is also Mrs. Helda in structure modification, yeah, of bioactive compound. Mr. Hanggara in photocatalysis for sustainable energy and environment, and Dr. Maktum also in the biofuel production, subcritical water process and waste processing. Also, we would like to thank our team for doing research with us. And also, finally, thank you very much for all the audience coming today. And if you have any discussion or suggestion, I will appreciate very much. Thank you very much. So please, moderator, Dr. Maktum.
Okay, thank you very much for meaningful insight about integrated recovery for bioenergy production, Dr. Rizky, my best friend forever. Yes, and as mentioned before by Dr. Rizky, we are a couple, yeah. Okay, as presented before, Dr. Rizky and her team are currently working on the production of biofuel, mainly biobutanol, from many kind of biomass waste, from agriculture waste to plantation waste. Dr. Rizky and her team have successfully developed an integrated green process to valorize various kind biomass into reducing sugar and bioenergy. Okay, interesting topic, considering that Indonesia is rich in natural resources that have not been utilized optimally. Okay, ladies and gentlemen, at this time, I would like to open the discussion section. But before I read some questions from participants, please allow me to ask Dr. Rizky about the effect of raw material characteristic used on your work. How does it make an impact on integrated recovery? Raw material characteristic.
Okay. Thank you very much, my husband, for very nice question. How the raw material impacts the separation? Yeah. We don't have the data yet, actually, but it is a very interesting topic, yeah, to be studied in our research. But I suggest that in our biomass, it contains some lignin, yeah, lignin, cellulose, and hemicellulose. It could be degraded, yeah, degraded to some inhibitors like furfural, and also furfural is from glucose, yeah, and from lignin there are some phenolic compounds. I think I don't know yet, actually, but not, I think not the feedstock will how to say, will affect the separation significantly, because compared with the extractant amount, yeah, it is very small, I think, in the media, like below 50 gram per liter. But extractant itself is very high amount. So I think the separation itself would help the fermentation, this inhibitor. Maybe we will study next time maybe about this, because like furfural, phenolic compounds, they are inhibiting the fermentation, and if we could separate it also from the media, we could improve the fermentation, hopefully. So maybe this integrated recovery will help the fermentation to be more flexible for many types of feedstock, I think.
Okay.
Is it okay to answer your question?
Thank you. As mentioned before, those degraded compound like hydroxymethyl furfural, and phenolic compound are inhibitor for fermentation. Yeah, research, yeah. Okay, thank you for the next answer. Maybe someone want to ask directly to Dr. Rizky, please. Okay, committed. Maybe I'll read the question from the summer school participant that have been collected. Okay, this is the first question from Dr. Hanya Sudrajat from Chemical Engineering Department. Biohydrogen from microalgae with extra is considered as a promising technology, but yield is typically still small. So what can be metabolic limitation for achieving useful yield? Dr. Rizky.
Okay. Thank you very much for the nice question also about biohydrogen from biomass, yeah, including microalgae and waste. what is the metabolic limitation for achieving appreciable yield? So in biohydrogen fermentation, acid is converted to hydrogen. The limitation in the metabolism is actually the mass transfer, the mass transfer of hydrogen during the fermentation. If the production of the hydrogen is too high in the fermentation, so the fermentation could not be long lasting. That's why we have to improve the mass transfer from liquid to gas. Hydrogen firstly produced in the liquid media and then transferred to gas. If the concentration of the hydrogen was too high and we don't do anything to our fermentation, so it will be low. The production of the hydrogen will be low. That's the problem. That's why we have to separate and give some external pressure. That's why we how to say, we recycle also the separated gas to give some sparging to the liquid. And then hopefully from that we can get more biohydrogen, improve the activity of the bacteria. Is it okay to answer to your question? Thank you. Okay, thank you. You're welcome, Pak Hanggara.
Next question, Dr. Rizky, from Mr. Krishna Kustinar from private sector. Great PPT material presentation. Did you have any intellectual property rights that have been registered and implemented in biochemical industry? Thank you.
Thank you very much, Pak Krishna. Oh, not yet, because I'm waiting, I'm still working with my research until the downstream process. And after we could apply the overall process, we still have some more to study, like upgrading the product, testing the product, and then testing the product in the engine, like for biobutanol maybe, and then scaling up. I still have to work with my team to meet the market requirement. So hopefully, if there are someone interested, and we can work together and support our research and commercial production, maybe. Thank you very much for the question. Maybe next time we will register some of our research. Inshallah.
Last question from Mrs. Arin from UNS. Plus 11 Maret. Thank you, Dr. Fitri. Do you know if I want to produce biobutanol, what a promising or suitable waste biomass feedstock I can utilize?
Thank you, Arin from Universitas Negeri 10 November, bukan 11 Maret. Yeah. Promising biomass should have lower lignin, maybe lower lignin composition, but it's okay. it depends on the pre-treatment process also. If the pre-treatment could remove the lignin efficiently, so we can get cellulose, glucose or other sugars. But so far, if we want to use lignocellulosic, our team has ever been studying about the paper pulp. It doesn't have lignin, only cellulose, so we can use it without pre-treatment. That's a good biomass. But if we want to use lignocellulosic, I'm still not sure actually. But a lower lignin is better because lower inhibition, lower inhibition in the fermentation and also hydrolysis. In Indonesia, there are so many types of lignocellulosic from the agricultural product. Usually, the drier the waste of the agriculture, the lignin will increase. So maybe the wet one might be better, maybe. Okay, that's all, maybe. Is it okay to answer your question?
Inshallah, enough.
Enough?
Yeah. Ideal material as feedstock for precision bioenergy is low lignin and high hollow cellulose. Yeah, high cellulose and hemicellulose.
Hemicellulose, yes.
Yes. Thank you, Dr. Rizky. Again, thank you very much for remarkable discussion. That is the last questions. Okay, ladies and gentlemen, please give a virtual applause to Dr. Rizky for the excellent presentation.
Thank you very much.
Okay, Dr. Rizky, I hope you and our son always healthy, Inshallah.
Amin. Inshallah.
Ladies and gentlemen, we have come to the end of this session. Thank you for your kind attention and participation. I hope you find it worthy and could help you to moderate in this young scientist session. We expect this event to be a decent platform for exchanging ideas to generate novel insight and produce impactful collaboration. Okay, we look forward to seeing you at next session. Assalamualaikum warahmatullahi wabarakatuh. Samantha, time is yours.
Okay, ladies and gentlemen, finally we got to the last section of this event, that is closing. As the master of ceremony, we would like to give thanks to Dr. Jakapon Pantuwakti as the speaker, to Dr. Rizkia Fitria Darmayanti as the speaker, to Dr. Insinyur Wahyu Hadianto STMT as Dean of Engineering Faculty Universitas Jember, to Insinyur Boy Arif Fahri STMT PhD as Head of Chemical Engineering Department, and to the audience entirely. May what we had conducted will be useful for us. If in guiding this event we made mistake or offend someone here, please accept our apologize. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.